Greetings, my viewers. My name is Adenata Supredi from Universitas Udayana, and today I'll be presenting about hardness test. So before we go any further, I'd like to do a brief explanation on the Vickers test. So what is the Vickers test? A Vickers test is a hardness test that uses a pyramid-shaped indenter and a load that ranges from 1 kilogram to 120 kilograms. And as you can see here, this is what the side of the indenter would look like if you were to see it from the side. And here is what the indentation would look like from the top. And as you can see here, load is P, symbolized by P. As I have previously mentioned, Vickers test uses a 1 to 120 kilogram load. So why do a Vickers test? We do a Vickers test to determine how hard a material is. And how are we going to determine how hard a material is through a Vickers test? We determine that by calculating its hardness number, or hardness Vickers, symbolized by HV. So as you can see here, to calculate HV, you will have to divide 1.854 multiplied by P divided by L squared, L being the diagonals. Alright, that's enough about Vickers. Let's get to the practical examination. So to do a practical examination, we'll first need a specimen. So here is what the specimen that we used look like. So what we do to it is we grind it down, starting from 600 grit, working our way up to 800, and then 1000, and then 1200, and then 1500. Why we do this? That's because a Vickers test makes such a tiny indentation that if you were not to grind it, it would be very hard to see. So that's why we would need to grind and then polish sort of the specimen. As you can see here, that's me grinding and polishing this specimen. This picture was taken after the test, so as you can see, some rust have accumulated on the surface. It used to be shiny. So to do the Vickers test, here is the equipment or instrument that we'll be using. I'll just do a quick and brief explanation of this equipment. So here you can see this is the microscope. You use this to see the indentation that you've made. And then here, right next to it, is the weights. This weight will push down the indenter right under it, right here. That's the indenter. Here's the diagram from before. And right under there is our specimen. If we were to zoom up, as you can see here, that is our specimen, and that over it is the indenter. Okay, so how do we make the indentation? Alright, so it's quite simple actually. To apply weight, okay, in order to make an indentation, you would have to apply weight onto the indenter so that the indenter would apply said weight onto the specimen, making an indentation. So how do you apply weight? To apply weight, first rotate the microscope until weight is positioned above the specimen. As you can see here, the microscope is positioned over the specimen. So what you're gonna have to do is you're gonna have to turn the weights and indenter and position it over the specimen, like so, as you can see here. And now to apply weight, simply turn the switch to let weight fall freely onto the specimen and let gravity do the work. Okay, after that we get an indentation. So here we did 3 indentations. Here's the first indentation, the second indentation, and the third indentation. You can sort of see the first indentation, and then the second, and then the third. So what do we do now? Okay, so what we do now is we measure the diagonals here, symbolized by L here, but we'll be using A and B for this. So first we measure how long A1 is on the first indentation, being this one. So here is all the data we've collected. For indentation 1, A1 is 3 stripes, so we use this to measure the diagonals. So this one stripe is equal to 0.1 millimeters, and this from 0 to 5 is equal to 0.02 millimeters according to the lab supervisor. So what do we do now? We measure how long A is, and then we measure how long B is, and then from there we can input said numbers into the formula, and we get a hardness Vickers number. So let's crunch the numbers. We got A1 is 3 stripes, and we multiply that by 0.1 as shown here, and we get 0.3 millimeters. And for B, we get 11 from here to right about there. That is 11, and we multiply that by 0.02, and we get 0.22. And that's not the end of it. You have to multiply that by 2, because as you can see here, B is not all the way from end to end. B is only half the way, so you would have to multiply that by 2 to get the whole diagonal. Do the same with A2. A2 is the same. However, instead of doing it vertically, you do it horizontally. So A2 horizontally is also 0.3 millimeters, and B2 vertically is also 0.44. So the mean, the average of our diagonal is 0.37 millimeters. And for the second indentation, we get 0.4, and I find this weird because we did not change anything. Maybe there was a mistake in our measurement, but we'll stick with 0.4 millimeters. And for our indentation number 3, we also got the same as indentation number 1. We got 0.37 millimeters for its mean diagonal. Okay, let's talk about indentation number 2. So indentation number 2 has the most abstract, not abstract, it has the most different data measurement than the other 2. So what I did was I input indentation number 2 into Imagy, and so I measured with this, setting this as scale. I measured 1, 2, and then 3, and what I got was, for its diagonal number 1, we got 0.362, quite similar to what we got for indentation number 1 and 3. And for diagonal number 2, I got 0.366. Also not that far, maybe because I made some error here, since I have to sort of eyeball it. And just in case, I also measured how long this would be, since I was instructed by the lab supervisor that this is scaled to 0.02. However, in Imagy, the result I got was 0.08, so maybe there was an error either on my part or their part, so I'll just add this to the calculation. And I input them into the Vickers hardness number calculator. For indentation number 1, I got this as the result, 135.456537 as the result. And then for indentation number 2, I got 115.899. Again, being very vastly different from the other two. And then indentation number 3, I got 137.456537. Not that exactly, exactly the same as indentation number 1. And then here I calculated indentation number 2 again, but now with the data I got from Imeji. And the result I got was 139.958942. More reasonable, it's more likely to happen instead of 115. So maybe there was a mistake in our measurement during the practical examination. Alright, so next we have a tensile test, and I'll be presenting about this tensile test also. Alright, so before I start, let me just refresh and review what a stress and strain curve is. So what is a stress and strain curve? Well, this is a stress and strain curve, stress being the y-axis and strain being on the x-axis. So what's this? Okay, so this is our specimen. So what happens here is you clamp both of its ends, and basically what you do is you pull it apart. So as you pull it apart, the specimen elongates and it extends, and we measure that. We measure its delta L, its elongation, and its stress, its load, the load being applied to the specimen. So what we will get from this is a load and elongation curve, and then from there you can convert said graph into a stress and strain graph using these formulas. Right, let's move on. So same as before, we'll first need to prepare our specimen. So what is this specimen? For this we'll be using aluminium AA6061, and this specimen has a length of 150 millimeters, and L1 and L2 where L1 and L2 is 40 millimeters. So this from end to end is 150 millimeters, and what we do here is we make a shoulder, sort of, to concentrate the elongation, and that's where the neck would appear. As you can see here, this is called a neck, and that's where the fracture would happen. So what you do is you first have to sort of draw what you want your specimen to look like, and then you just grind off the materials so that it would look like this. R is supposed to be 12.5. However, due to human errors, it's not very uniform, but that's okay. Completely normal, since we have to do everything by hand. So we'll just have to carry on with the experimentation. And here is the instrument that we'll be using. Let me just briefly explain what the parts of this instrument are. So right down here we got a hydraulic jack. What it does is it pushes this inner square up, elongating the specimen. And this right here is a micrometer dial gauge. What it does is it tracks the elongation, the elongation that we apply to the specimen, So, and then above it we have a digital weighing scale. So this reads the load that we are applying to our specimen. However, this is in kilograms, so we'll have to later convert that into Newton. Alright, so right there in the middle we have our specimen clamped using wedge grips. So what you do now is you extend the hydraulic jack so that this inner square would go up and force our specimen into elongation until it eventually fractures. While we do that, we would have to take note of the displacement here and the load being applied. So now we arrive at this data. We got first data for specimen number 1. As you can see here, this is not as perfect as the graphs you saw here. That's because this was done with a hydraulic jack and clamped using non-conventional clamps. So you can probably tell this what's probably happening here is the specimen slipping from the clamps, giving off either more load or more elongation. It really depends. So my hypothesis is that the clamps are slipping from off of the specimens. That's why we're not given such a clean graph, but more or less it's quite presentable. So as you can see here, this is probably the plastic region, and right here elastic region, and right there it sort of starts moving into the plasticky regions right around there, and then it eventually fractures right under 300 Newton per millimeter square. So that's where the fracture happens. This is for specimen number 1, with its ultimate tensile strength being 300. That's right about there. And yeah, next we have specimen number 2. Not that different of a story, also not the best graph you'll find around, but this is also quite presentable. This is the elastic region, and then this is where it starts to become plastic region, and this is where the specimen starts inhibiting plastic so here is probably where the ultimate tensile strength lays, right around 304 Newton per millimeter square, and then it fractures at around 304, right about there. And next we have specimen number 3. So I'll have to explain why we have so many zeros here. So what's happening here is, as you can see, the displacement, the delta L or elongation keeps going all the way to the 11th entry, and the load is still 0. So what's happening there probably is, as I have previously mentioned, the specimen is slipping. So it sort of slipped as far as 1 millimeter. So no elongation actually happened there to the specimen. However, the scale kept reading that it was being elongated. So that explains the constant zeros here in the weight and the load. yeah, that's it for specimen number 3. Here you can sort of see more clearly the elastic region, and then here's the plastic region. Here's the ultimate tensile strength. This is probably where the neck starts to appear. However, being such a light and brittle piece, you don't really see that long of a neck, so it just simply fractures there at 291 Newton per millimeter square. So that's all I have for today. Thank you for watching.